Hi folks, this is lecture 16 of the mechanical vibrations course, and what I have on the agenda today is described in the following items. Response to an arbitrary input, response to a single degree of freedom system to an arbitrary input, the development of what is called a convolution integral or Duhamel integral, which pertains obviously to item number one. And finally, the response of a single degree of freedom system to an arbitrary periodic input. Now, it is worth reflecting back and see what we did in the past 7 weeks. So the first 3 weeks of the course dealt with free vibration. In other words, there was no forcing function involved. We had the mother of all equations, namely mx double dot plus cx dot plus kx equal to 0. Now, the fact that it's equal to 0 means that there are no external forces applied to the mass. And of course, there are initial conditions involved. For example, given initial position, initial velocity, we can go ahead and solve that thing, and we did it in its entirety during the first 3 weeks. Then the next 3 weeks, essentially what we did, we said, okay, why don't we apply a force, external force to the system? And that means the right-hand side of the mother of all equations is not 0 anymore, but it's a function, a force that depends on time. For example, f of t, okay? But at that same point, at that same time, I indicated that we are not going to look at an arbitrary function, but we're going to specialize to a very special type of function, which is called harmonic or sinusoidal forcing term. And what I mean by that is that the right-hand side is of the form f naught, a constant, times cosine of omega t, or f naught times sine of omega t. We refer to both of them as sinusoidal. This omega on the right-hand side is what was called the driving frequency, obviously, of the force. And this type of loading actually is very common. For example, whenever you have a rotating machinery, fans, propellers, compressors, etc., because of the unbalance in the general unbalance in the rotating component, there is always a harmonic force applied. And in the case of, for example, let's say a single degree of freedom system, you can imagine that there is a motor that's turning, and it's sitting on a mass, and it's exerting that unbalanced force in the form that I mentioned to you. Okay. We spent 3 weeks solving that and coming up with all kinds of scenarios and all kinds of graphs, etc., etc. Now, in the last lecture, I said, why don't we, instead of taking a harmonic force, why don't we take a very special type of a force, which is a force that is alive over a short duration force. Obviously, maybe before that duration, the force was not there. After that duration of interest, the force is not there, it's 0. But during that period of interval, short period of interval, there is a function. There is a forcing that starts from 0, goes to some maximum, and then drops down to 0. We call that thing an impulsive force, okay? A short duration force, now the word short duration by itself is a loaded word, short with respect to what? And that was actually brought up in the last lecture. But anyway, let's move on. Impulsive force, and we made that very simple by looking at it as essentially a rectangular pulse. In other words, instead of making an arbitrary force going from 0 to some maximum and dropping down to 0, we pretended that over that duration, the function was present, the force was present, and it was a height, had a height, and I referred to that height as f hat, constant height, f hat, divided by 2 epsilon, and the width of it as being as 2 epsilon. And I said that short duration means let epsilon goes to 0. So when you do that, the peak actually goes higher and higher and higher as epsilon goes to 0, and the width is going smaller and smaller and smaller, but the area under that curve is always f hat. Okay? So we think about this thing as an impulse of magnitude f hat because the area under it is f hat, and it's over basically 0 time interval, applied over 0 time interval. It's a mathematical tool. It's very useful, but one cannot make sense out of this whole thing in a sense. So we call that thing an impulse force of magnitude f hat, and in the event that this f hat, in other words, the area under the curve, under that rectangle is 1, or area of that rectangle is 1, we call it, give it a very special symbol, and call it delta of tau, which means that a function that is 0 everywhere except at the point tau, it shoots to infinity at the point tau, and the area under it is 1. It could be that tau is actually 0, centered at the origin, and people in that case refer to it as delta t, Dirac delta function. And we spent the entire period last lecture and devoted it to looking at the solution when the load on the right-hand side of the mother of all equation is a delta function or an impulsive force. And I mentioned to you that the only effect that this impulsive force will have on the mass, it changed its initial conditions, initial velocity, in fact. Okay, because after all, it was not there in the past. It will not be there in the future. It's only during that infinitely small time interval that it has a value. Now, we got the solution to that equation. The whole lecture basically was devoted to that, and we came up with this thing which is called impulse response function. In other words, when you apply an impulse to the mass, how does the solution look like? We call that solution, if the magnitude of impulse is 1, in other words, if f hat is 1, we called it unit impulse function, but did not always use the word unit. It's an impulse response function, and denoted by h of t, which had an expression. That expression, you can go check it out, and you see it again today. And I also said that, yes, I mean, if this impulse was applied at a different point in time, not at t equal to 0, then we call this the response, again, impulse response. However, the form of it is going to be h of not t, but t minus tau if the impulse is applied at time tau. And I mentioned that you may not see why this is so important, because it's going to come back and haunt us, or it's going to come back and help us when we try to solve the same problem where the load is an arbitrary function f of t, when the force is an arbitrary function f of t. And that's the uh, crux of the lecture today. Have fun. Okay, so here's the situation. Suppose we have a function that is given on the top and it is arbitrary. You see that it changes in a very arbitrary manner. Now, if you think about this function, if you take a very small, narrow strip of this function, which is drawn down here, and you just look at it, you see that, oh, wait a minute, I recognize this force over a short duration. Isn't that an impulse? Have I not done this problem on Thursday? And the answer is yes. So if you have an arbitrary function, the whole idea is you break it up or you view it as an infinite number of impulses applied at different points in time. For example, this impulse is applied at t equal to 0. This impulse is applied at time equal to something else, maybe halfway between these two, etc. So this is why we actually discussed, when we discussed this thing on Thursday, I pointed out, let's look at an impulse which is imparted at an arbitrary time, tau. Tau may or may not be 0. Okay. So here's the situation. We look at it at one of these impulses that you see here. Let's say that it is imparted at time ti, which would have been tau equal to ti. Okay, and we know what the solution of this problem is. On Thursday, I showed you if you had this one impulse, the solution to this problem would be take the magnitude of the impulse, which is f times delta t. F times delta t, look at the unit of it. It has the unit of impulse in force times duration, times the impulse response function, which is shifted by the amount tau or by the amount ti. We did this thing on Thursday. So if you take the magnitude of the impulse, f times delta t, and you multiply it by the impulse response function, remember that function h, but shift it, namely apply at time ti, that is going to be the solution due to this one particular impulse. Now, to get the total impulse, of course, you have all of these heights, all of these peaks, all of these spikes, okay? You have to add it up. And that's what we did, because we're dealing with a linear system. If you find the solution due to that particular thing, and you find all other things, to get the total solution is just the sum of them. Now, this looks familiar to you. In your calculus class, the integral calculus class, when you had sum of a bunch of things times delta t, as these width went to 0, didn't that give you the integral of f times this? Yep. That's exactly what you did in your calculus class. So the total response of the function due to an arbitrary load is just take the load, multiply it by the impulse response shifted by the amount tau. This is called convolution integral or Duhamel integral, by the way. And look, we have the impulse response function in it, and that's what I promised you on Thursday. This impulse response is going to come up for an arbitrary distribution of the function f. Okay, so that's exactly what I just said in writing. Now we go here. So if you have an underdamped single degree of freedom system, we actually found out what h was. Remember, we actually had an expression for it. And that expression, please go ahead and look at it. H of t, just h of t, okay? Not h of t minus tau, because t minus tau, all you do, you go to t, every time you see a t, replace it with t minus tau.
So h of t, please go to your notes, was 1 over m omega d e to the minus zeta omega n t sine of omega dt. In other words, right here, you see, right here, 1 over omega d divided by this. Now, if I want h of t minus tau in that expression, I can replace it with every occurrence of every occurrence of tau that I see here. Okay, I replace it with t minus tau. And there's two ways of doing this thing. One, you can introduce the shift in f, like here. The other one, introduce the shift in the impulse function. Notice that here, if you introduce the t in the impulse function, you're going to get sine of omega dt minus tau. But in front of it, there is e to the minus zeta, okay, omega n times t minus tau. But t does not depend on tau. That's why it's brought out of the integral. If you have any questions, please see me or please discuss it. Okay, now notice that I'm assuming when you do this thing, I'm assuming that the initial conditions are 0, because think about it, the impulse response function assume that initially t is 0, at t equal to 0 initially, x is 0, and the velocity, now of course it can't be 0 if you have an impulse, the velocity is going to be, impulse divided by m. But when you write the general solution to the equation with an arbitrary f on the right hand side, if you claim that this is the solution to x, notice that this assumes that x of 0 is 0 and x dot of 0 is 0. And it's not easy to see because look, if you put 0 for t, you have integral from 0 to 0. Well, that's 0, so x of 0 is 0. If you differentiate x of t, you differentiate integral with respect to upper derivative, upper limit, not derivative, upper limit. All you do in here, or in there, you take the integrand. There's the integrand. See that? There is the integrand. There is the integrand. Okay, or there is the integrand. You write the integrand as the derivative of this. Okay, and then you plug in t equal to 0 in it. You see that you're going to get. See that you're going to have sine of omega dt. If you differentiate this. If you differentiate this with respect to t, it's going to be f of 0, right? F of 0, because you plug in every time you see a tau, you replace it with a t. So it's going to be f of 0, e to the minus zeta omega nt. And here it's going to be sine of omega dt. And we set t equal to 0, this will kill the other terms. Moral of the story, as long as the initial condition is 0, when you write the expression like that as this or that, it means that you're assuming x of 0 is 0 and x dot of 0 is 0. By writing it like that, those are true. And just remember that this shift can be either in f or it can be in t, and that's what this is saying. By the way, this guy was alive about 100 years ago. Okay, so 50 years ago. So these are all relatively new stuff in the grand scale of things, civilization. These are very recent. Okay, let's do an example. Suppose our loading looks like that. The right-hand side of the equation is 0 up to some initial time t naught, and then it takes a value f naught. What we want to know is what is the solution to the equation. Think about it like this. You have a mass damper system, and you take a weight and drop it on that mass. And the weight or that thing that's being dropped sticks to the mass. Well, you know what's going to happen. The solution is going to be something like that. So you suddenly apply a load, the load being the weight of that object. You suddenly apply the load, the weight of that object at some time t naught, and the mass will start vibrating. Okay? So what you want to know is the solution to this step function. I mean, it could be that T naught, we are assuming that T naught is 0. It's just that it's basically a flat line starting at T equal to 0. But it doesn't have to be. It can be up to a certain time. So I'm going to look at the expression like that, okay, instead of saying that, hey, we apply this thing initially, T naught equal to 0. So the right-hand side of the mother of all equation is this function. And this function is 0 up to time T naught. And then a fixed value, maybe the weight of the object that you dropped onto that mass, maybe something else. What is a constant after that? Well, initial conditions, we are assuming that they're 0. Obviously, when you drop this weight on that mass, right before it hits it, we are assuming it's an equilibrium position, so x naught is 0, and right before it hits it, velocity of the mass was 0. Okay, so we can, because of that, we can write the solution like this. So here I decided to put the shift in the impulse function, impulse response function. And don't let it bother you, because 2 slides ago, the e to the minus zeta omega and t was outside. M omega t was outside. E to the minus xi omega and t was outside, because the integration is with respect to tau. But if I kept it in, I'd like this actually better than the way it was written 3 minutes ago, because it's easier to see what's going on. The shift is in t minus tau. So integral from 0 to t, this is the shift that I was talking about, shift in the impulse response function. So we're going to break it up into 0 to t naught, but from 0 to t naught, f is 0. This is 0. This is f. From 0 to t naught, f is 0. And then from t naught onward, f is a constant function, f naught. So this will go away, and I have to integrate this. Now, you can look it up in a table of integrals. This requires integration by parts, or leave it to you to go and check it out. Okay, use a table of integral or do the integration by parts with respect to tau, and you can get this integral, and you clean it up. It's going to come out to be like that. Now, just notice that if T naught, first of all, if there is no damping, zeta is 0, right? So theta is 0. So this theta is not going to be there. Okay, just keep that in mind. And if T naught is 0, T naught is 0, initial time is 0, this even simplifies further. But in general, that's what it is. I mean, you don't have much choice. You have to know this formula. Okay? It's written here for your convenience. If T naught is 0, in other words, you drop the mass, drop that weight onto that mass, and measure time from there on. Okay? This thing, well, that's good, because the T naught is just going to go away. This T naught is going to be 0, and this is going to be 0, etc. So it looks like that. Okay? And by the way, notice that what happened, I put some numbers here for you so that you can actually plot this function. You can plot that function, and it's going to look like this. Look, if this was a static problem, if you took the force F naught and applied it to the mass, it will go down by how much? It will go down by F naught over K, by this. That is the static deflection, right there. If you apply a force of F naught to the mass as a static problem without causing vibration, you put your hand on it and gradually push it down. Apply the force of F naught, this is what's going to happen. But if this is suddenly applied, then it's going to be vibration about that steady state condition, about that static solution, and it's going to look like so. So this plot that you see here corresponds with these values. Now, those of you who have either taken control theory or will be taking control theory later on, you'll notice that some terminology will pop up. This is called overshoot. This is called overshoot. This height is called overshoot, the peak response. And after a while, this plot is going to be within some percentage of the actual F naught over K, and that's called settling time. So the place where the time, it puts the curve in between some percentage value, maybe 3% of the final value, or 2% of the final value, that's called settling time. You'll see that, okay? So here's what I was just talking about. Overshoot is this height, and the settling time is you decide what percentage of this F naught over K you want. For example, 5% of the final value, as long that the place where the curve is going to stay within that 5% up and down is called settling time. Now, for the case of the place where this peak occurs, that's very and t equal to 0 incidentally, you can see that. You can actually work it out. This is an exact value. So if you know omega d, okay, this point is pi over omega d. Okay, so for this particular problem, and if this percentage is this overshoot, if this percentage overshoot is 3%, then you can find out what this TS is. Now, if you choose a different percentage, 5% or 2%, this will be either to the left or to the right, and it's not going to be this value. Okay, and this is only approximate. Okay, so but this one is exact. TP is exact. Settling time is approximation. Okay. Okay, let's do an example here. So we have a truck, and this truck is being loaded. And obviously, if you apply a load here, this truck starts vibrating up and down. So it can be, at a very crude way, approximately a single degree of freedom system. So the mass of the truck, okay, and the load that is being dumped on it, suddenly is going to be the mass of the material in that bucket times G, and it's going to be applied suddenly, okay, and this starts to vibrate up and down. And essentially, if you just design the springs for a static load of MD times G, you may be underestimating the values of K, and it may actually destroy the springs, in a sense that it makes the springs deform more than what you designed for, and therefore cause a problem. So now notice that if you go back to the previous slide, you see that that peak had a much higher deflection than the F naught over K. Okay, but so what you want to know is the response of the single degree of freedom system, or this truck, because of suddenly applied constant load. Just like that. Okay? No load, but suddenly MDG. So it's like that. Okay? And we know what the solution is. Solution, just have to write it down. So this is going to be F naught over K minus F naught over K times this. Okay? Now, if there is no damping, if I ignore damping, things are going to be a lot nicer. So this zeta is 0, so this is going to be gone. Okay, and theta is 0, and theta is 0 because if I applied it initially. Now, theta is 0 because T naught is 0, you know that. Okay, and then omega D is always omega N if there's no damping. So there we are. So look, the maximum deflection of the truck is not the static one, is double the static one. So if you design your design your spring stiffness based on MDG over K, static load, you're missing this factor of 2. So you've got to be very careful not to under-design because you just assume that this was a static load. Because you assume that the load on the truck is just MD times G, the weight of the bucket of dirt that is being dumped into this. So let's look at a different situation where this is actually a finite duration pulse function. Now, this is not short duration necessarily. This is not short. If this was short, then this would be an impulse function. Okay, that's what we covered last Thursday. But this is a finite duration, constant value of the force applied. This is called pulse function, pulse signal. Let's assume that the initial condition is 0. So the way you solve this problem is look at this thing as the sum of two forces. Just look at it like this. This force, constant, plus the negative of this force, constant. If you add these two up, you get exactly what's on the left. So we know the solution to this. We just spent about 8-9 minutes on it. Just a minute, just before this. And we know the solution to this, again, part of that 7-8 minutes that we discussed, is minus F naught, but at time t1. So just write those two and then add them on. So the total load is the sum of these two loads. We know the solution to F1. We know the solution to F2. Okay? Just write down X1 and X2 literally. You just have to patiently write them down and you get your answer. No, I didn't do that. I'm going to take a short. Okay, so I'm going to be solving another problem for you. It's a trash compactor. So what happens here, you have a mass spring damper system, and this cam is moving to the left. Notice that as it moves to the left, it pushes this handle down, and this handle is what's causing the force to be transferred to this mass. And notice that the force is not constant, because the further this goes to the left, the more this is going to get pushed down, and the more force is going to be applied. The moral of the story is that the force is not constant anymore. It's linearly varying. Incidentally, the slope of this line, force versus time, is the same as the slope of that curve, proportional to it. Let's put it that way. Okay. Now, really, it's proportional to it. Assuming this is going at a constant speed, this is proportional to it. Constant speed. Now, the response of this problem is ironic, but x of t, this mass, begins to oscillate. As this is moving to the left at a constant speed, this mass begins to oscillate up and down, and the response of it, the displacement of it, is actually like so. In other words, yes, it is following that line, the trend of that line, but it oscillates about that. So to do the problem, to get this curve, we're going to assume that damping is 0. Otherwise, there's more things to be done. So let's see now. If you look at the small, well, let's look at it like this. If you look at this diagram, okay, the value of the force imparted is the slope of this line times t. Okay, when t is 0, no force. As t gets bigger and bigger and bigger, more force, and this is the relationship between the magnitude of the force and the slope of that curve, which incidentally has to do with the slope of this curve and the velocity of that, constant velocity of that. Now, we know if f of t looks like that, how to calculate it. So generally speaking, no damping. You write down the Hamilton integral. Remember, the shift in tau can be either in f, or it can be in the impulse response function. So either you write this thing as f of tau sine of omega n t minus tau, or you write it at f of t minus tau sine of omega n tau. Either way. But we know what this expression f of t minus tau is. It's right here. You just plug it in and clean it up. You split this thing into two integrals, so delta f times t, which is a constant with respect to tau. That's where it came out. And then delta F times tau sine of omega n tau. You cannot take this tau out, okay? The delta F you can take out, but not the tau. Now, this one is easy. You know what it is. It's cosine, right? 1 omega n cosine. This one you have to integrate by parts or look it up in a table. For example, integral of, I don't know, tau sine of 5 tau. Okay, so you have to do integration by parts or look it up in integral, and this is what you're going to get. Very neat. So notice that the solution is, of course, this linear variation. This first term is that linear variation, and on it there is this sinusoidal thing superposed. So when you add them up, you get basically a sine curve, kind of a sine curve going up along that line. Okay? Some general comments about arbitrary load excitation. Note that the response of a single degree of freedom system to an arbitrary input can be calculated numerically. For example, even if you cannot do the integral, that Duhamel integral, that convolution integral, even if you cannot numerically, if you cannot integrate it exactly, once you give me the t, I have basically an integral over a given time of some garbage. I'm sorry, not garbage, some stuff. And you know, you can give it to a package, or you can do the numerical integration yourself and get the value. So you don't necessarily have to know how to integrate that exactly, because it may not be possible. Like in these examples that we just did, we had the integral of tau sine tau, something like that. And there are tables for it. You go find it to integration by part. But if there's something there that is not feasible to do it analytically, you can still do it numerically. You can do the integral from 0 to 7 of tau sine of, or tau cube e to the tau sine of whatever tau numerically. You can still do that numerically. Now, the response calculation for general external loading does not include response that might exist because of non-zero initial condition. What this thing means is that when we wrote this as the solution to our particular solution, the assumption is that initial conditions are zero. So this tells you that the initial condition is zero and initial position is zero, initial derivative is zero. If that is not the case, then you have to add to that the solution to the homogeneous part. And this is the stuff that we did, essentially in the first 3 weeks of the course. Right? This is due to no load. Homogeneous means that no load on the right-hand side, and the solution looked like that. So basically, you need to know X naught, you need to know V naught, and the solution is going to be this piece, which imposes the initial condition, plus that piece, which has zero initial conditions. Okay? Right. So note that the effect of applied force, that means this F, on the homogeneous response is not present. And F has no impact on this piece. On the first two pieces, it has no impact. Okay? Because the value of the convolution integral, because this at t equal to 0 is 0, and the derivative of this at t equal to 0 is 0. Okay, that's why this F has nothing to do with the actual initial condition if there is, it's given to us. So in general, if you do have the initial condition specified, the solution is going to be like that. Okay, this XP is right here, this XP is right there, this is your XP, and A naught, A, and B are calculated from these expressions. Just plug it in. There's your A, there's the B. Okay? Now, so basically this is what I was referring to. So let's read this thing carefully. If the particular solution XP or its derivatives do not vanish at t equal to 0, but this one does. Look, this one does. If we use Duhamel integral, then both x of p of 0 and x dot p of 0 is 0. But if this was not Duhamel integral, you really have the effect of xp at time 0 and xp dot at time 0 in A and B. Okay, we don't have to worry about it here because this at time t equal to 0 is 0, and the derivative of this at time t equal to 0 is 0. Okay? In other words, this is 0, and this is 0. And that's why if you use the Duhamel integral and you have initial conditions, there you are. There is your A, x naught, and there is your B, V naught over omega n. Okay. That takes care of item 2 on the agenda, Duhamel integral. Now, what if the right-hand side of the equation, the mother of all equations, is not 0, is not sine or cosine, is not an impulse function, but it's of a very special type, namely a periodic function. So, like that. This is neither sine or cosine, nor an impulse, nor an arbitrary general curve that you have on the right-hand side, and obviously it's not 0. So this is where we have to use the concept of Fourier series. Now, Fourier series, you have done it. Usually people in the math courses, they don't have the time to cover that. So later on, when you take some other engineering courses, you may end up, your engineering profs teaching you how to do Fourier series. Okay, so here's the situation. The idea is that if you have any periodic function of period t, here's an example. You can always break it up into a constant, a naught over 2, plus a whole whack, infinite number of cosine terms, plus infinite number of sine terms. Now, first of all, this omega t here is the period of let me see now. T is the period of this function. So 2 pi over t is the frequency of this function. Omega t is called fundamental frequency. You give me the period, I give you a fundamental frequency which is called 2 pi over t. We know that. Now it's the sum of sines and cosines of multiples of this fundamental frequency, omega t. So, how do you find A naught? There is a formula. You go to the interval 0 to t, forget about all the stuff on this side, just from 0 to t, one period. You do the integral, multiply it by 2 over t, that's your A naught. If you want to find an and bn, for example an, take the function f of t over one period, multiply it by cosine of n. This is a number, just a number. N times that number, omega t, times t, and integrate it. Now, if f of t is ugly, this is going to be an ugly interval, okay? Ugly integral. You may have to use a trigonometric, you may have to use a bunch of tricks from integration, or you have to look it up in a table, something like that, or numerically do it. And the same thing with bn, okay? So this is a laborious process, by the way. In other words, to find A naught is easy. It's basically the average value of the function over that, pretty much over that interval, almost double the A naught is double the average value of this function over that interval. Okay, you can see that right there. But these things take time, and in fact, it may be impossible to do analytically. Okay? You can always do it numerically. Whenever you have an integral, you give me inside, I can do it numerically regardless of how ugly these things are. Now, a couple of things you have to realize is that if the function that you're taking, if this function, if you plotted it, and if it's even, in other words, even means that the line, this vertical axis, is axis of symmetry of the periodic function. Both on the right and on the left, they look identical with respect to this. Then you're guaranteed that there are no sine terms present. If the function is even, which means the function is symmetric on the left and right, they're mirror images of each other, you're guaranteed that there are no odd terms in it, there are no sine terms in it, all the bn's are zero. On the other hand, if the function is odd, if you plotted this periodic function and the origin was the point of symmetry, in other words, you took one point on this side, connected to the origin, continued it down until you will hit the curve on the other side. Okay, that's called an odd function. Then you're guaranteed that there are no an's in the term. All of these are zero, including a naught. Okay, so these are very important observations that make your job quite easier in doing the calculation. So let's do an example. Here's a function. If you look at this function, it's periodic. Now, I have not drawn the rest of this thing for you, but it is obvious. It is obvious that things on the left and the right, if I draw a few more cycles of this, things on the left and the right are mirrors with respect to that line, vertical line. That means this is an even function. That means there are no signs there, guaranteed. I mean, obviously, this is in one period, going from one period from here to here, this is one period, the solution. Literally, you can write it from 0 to t over 4, from 0 to t over 2, it's a straight line right there with a slope of 4 over big T. And on this side, the slope is negative, and you can literally write these down. But you notice that this is an even function, therefore there are no sine terms. All the bn's are zero. Now, the average value of the function, you just work it out. The average value of the function, please just draw one of these cycles. Okay, notice that draw one of these cycles if you prefer, or just look at 1, 0 to t. This is positive, this is exactly the same number, negative, negative, positive, positive, negative, and when you integrate, it just happens that a naught will come out to be zero. There is no guarantee that a naught is zero. But in this particular problem, the average value of the function, integral from 0 to big T of this thing, because of the nature of the curve, they're zero. The sum, that integral is zero. A naught happened by coincidence to be zero. Don't get the impression that if your function is even, a naught is always zero. It's not. For this particular function, the way it is zero. And an's, okay, so an, so you break it up. If you have to integrate from 0 to big T, you break it up from 0 to t over 2, big T over 2, because the formula is there, plus the integral from big T over 2 to big T, so the formula is right there, and just literally hammer it out. There's no easy ways to get done. This requires integration by part, t times cos omega t, that kind of a thing. And t again, t times sine of omega, well, cosine, not sine is gone, cosine of, these have to be worked out. There are no easy ways, okay? And if you do it carefully, you see that these an's for even n's, including a naught is an even n, right? Including even n, including a naught, these are all zero. It just happens to come out to be zero. And for all odd n's, it comes out to be this. So we found the Fourier series expansion of this function. Now, let me write it down here for you. It's written down here for you. Written down right there. And if you plot it, if you plot just the first term, add the second term to it, add the third term to it, you see that as you take more and more and more of these, this Fourier series gets closer and closer to that, sudden discontinuity like that. So if in the limit, if you get infinite number of the Fourier series, all the terms in the Fourier series, all of them, then you get line, line, line. It'll never be that. You can't go to infinity. Infinity is a man-made or human-made tool. Okay, now let's look at some problems here. Here is a base motion. mass spring damper, and the base is attached to this cam, and the cam is turning. When you think about it, just literally you have to sit down and think about it. The motion of the base looks like this: sudden drop, sudden drop, sudden drop, because of this sudden drop in it. So this cam produces this kind of a displacement. This is not the force, but it's the displacement, okay, on this on this mass. If your cam actually looked like that, with sharp drops here, I mean, literally you can't have sharp infinite drops, neither here. There's always an angle, there's always a corner here, etc. But if you had it close to this sharp drop, then it's going to create these pulses, okay? So this is a periodic function. This is a period. If you want to know the response of this mass under this cam or under that cam, you have no choice but to do Fourier series of these functions. Now, I haven't told you actually. You can take any function and represent it with any periodic function and represent it with Fourier series. We just did it, right? But the question is, how does that help us to solve our mother of all equations? But all I showed you is that if you have a periodic function, how to write it as a Fourier series. Now the question is, what about your mass vibration problem? Okay, so here's the situation. F of t periodic, no problem. So the right-hand side is periodic. I can take this f of t and I can write it as Fourier series. Now, if I didn't have that infinite series, just had a naught over 2, would you be able to solve this equation? The answer is yes, of course. Okay? So, I mean, look, mx double dot plus cx dot plus kx equals to constant. If I know a naught, then I can get the solution to this equation. First 3 weeks, well, I mean, no, this is, we just discussed it. A naught constant, you can use, for example, integral to Hammond integral to get it. You don't have to go there, but this is a very simple problem. If you insist, you can go get x naught. Now, if I take one of these terms, for example, cosine of omega n big T t, this is the stuff that we did. Mother of all equation equal to a coefficient times cosine. It's the stuff that we did in the latter 3 weeks of the weeks 3, 4 through 6, right? The right-hand side was very special type, sine and cosine. Cosine is right here, okay? This piece is coming from the constant. This piece is coming from taking one of these terms. Can you solve this? Yes, weeks 4 through 6. What about the other one? Yes, the right-hand side is this, weeks 4 through 6. And then you can do any one of these, you can get the infinite series. Response due to the infinite Fourier series expansion. Okay, now you can see that this is not hard. If I tell you the first 3 terms, then you just do 3 of these. The constant, the cosine, and the sine, and then add them up. Obviously, what you get is not going to be the complete true solution, but it's going to be an approximate solution to the periodic problem. So let's do a few things here. So this kind of a function, this is a periodic function. If you did an analysis of that, you will actually notice that it's the sum of 3 sine terms, okay, with different frequency. Frequency 1, I mean, in hertz, 1 hertz, 4 hertz, and 7 hertz. This is called digital signal processing. In other words, you have a curve as a function of time history, and you break it up into its sinusoidal component. Now, obviously, this is periodic. It looks like it's periodic. Therefore, there is only, and consisting of only 3 terms, okay? Because in general, if you have a periodic function, there's infinite number of sines and cosine. But it's kind of deceiving, because this particular periodic function is only the sum of 3 sines sines or cosine, depending on how things are. So if you think about it, in the time domain, this curve is plotted here, time domain, and it's really made of three sinusoidal function. One of them with frequency 1 hertz, the other one frequency 4 hertz, and the final one 5 hertz. If you add these two up, in the time domain it looks like that. In the frequency domain it's just three spikes. Three spikes. This is why when you have an FFT analyzer or a instrumentation, you can ask it to take a signal that's coming out of an accelerometer, perhaps, show it to you in the form of a time history, which may be totally useless, or in the frequency domain, which may be some spikes. Now, in real life, these spikes are not like that. They're just going smoothly up or smoothly down, and a bunch of jagged stuff here, smooth up, smooth down, etc. So you've got to be careful. If you look at this problem, this is definitely not a finite number of sines and cosines. So if in reality, if you look at the time domain for Fourier series, it's going to be like that. But it's made of infinite number of frequencies. Remember those fundamental frequencies, omega, n omega t, right? Multiples of those, okay? And they're appearing here. This never stops. It goes all the way. But notice the height is getting small. The coefficients, an and bn, are getting smaller and smaller. This is why if you take enough of the terms in your Fourier series, the things that you left out, yeah, they don't contribute that much because those are very small, and you multiply it by sine and cosine of the same n, corresponding value. You left them out, but they're not going to make that much of a difference. They may not make that much of a difference. Now, what if the function on the right-hand side is non-periodic? Obviously, you can do the Duhamel integral. We did that. That was item number 2. But there are other ways of handling such problems, and that's called Fourier transform. So for a non-periodic function, there is no Fourier series, but there is something called a tool called Fourier transform, which is very closely aligned with that Laplace transform that you did in your course, in your differential equations course. Now, if you give me a function f, little function f, non-periodic or periodic as a matter of fact, but let's say non-periodic, I can do this calculation and I get something called Fourier transform of the little function f. And the inverse is true also. If you give me the Fourier transform, I can do almost the same kind of integration except that this minus is becoming plus, and I recover the original curve. Okay, so Fourier transform, everything is done in complex domain, and then this is a bit more difficult to digest than the Fourier series. It's the same thing, but and here's the guy. Look, 150 years ago, 150 years ago, 140 years ago. This is not a long time ago. And as I mentioned on Thursday, this is not going back to the Babylonians and the Greeks and the Roman and the Persians and the, thousands of years ago, or the civilization in China. This we're talking about 120, 130 years ago. Okay, in this case, almost 200 years ago. Okay, so here's an example of the function. If the function is pulsed like that, the Fourier transform, pulsed like this, the Fourier transform is given like this, and if it's a shifted one, it's going to be a complex. It's going to have a complex a Fourier transform. There's a real part and imaginary part, and we don't cover Fourier transform in this course or in your undergraduate curriculum at all. Electricals might do that, but yeah, that's not even the case at the undergraduate level. I mean, they might have seen the fundamentals of it, what it means and things like that, but these are really a bit more advanced and reserved for your graduate career. Okay, so that's it